All right. In this video, we will be going over section 4.3. Section 4.3 is about definite integrals. First, I want to give you a motivation about definite integrals. Suppose you are given a function f of x is equal to x squared on the interval 0, 1. And if I graph the function f of x, you will get a graph like this on that particular interval 0, 1. And then remember, last time we were talking about how to approximate the area under a curve. Okay, we can approximate this area under this curve by a bunch of rectangles. Okay, that's what we did last time. We used various techniques. Okay, we used upper sums, lower sums, left sums, right sum, trapezoidal sum, and so on. So here is the approximation of this area using upper sums. As you can see, in each interval, I divide this interval 0 to 1 into a bunch of sub-intervals. And in each interval, I complete a rectangle so that the height of the rectangle is the maximum value of the function in that interval. For example, if I go to this interval, in this interval, the maximum value of the function is this height, right? So I take that height to be the height of the rectangle and complete the rectangle there. Likewise, if I complete all the rectangles, taking the maximum height in that interval, I get the upper sum. Okay, these are the upper sum. Actually, this is also an upper sum with 50 rectangles. Okay, you have a finer mesh here. You have an even finer mesh over here with 100 rectangles. As you can see, when the width of your rectangle is getting smaller, you get a better and better approximation for the area under the curve. This gives a better approximation than this one. And of course, this gives a better approximation than the previous one. Okay, so smaller the width of the rectangle, the better the approximation. Okay, and here is the lower sum approximation. What do you do in the lower sum approximation? You divide your main interval into a certain number of sub-intervals. And if you go to any sub-interval and you take the minimum value of the function in that sub-interval, obviously the minimum value in this interval is this height. And with that height, you complete a rectangle in that interval. Okay. And then if you complete all the rectangles for all the sub-intervals, then you get the lower sum. Okay. As you can see here, if your function is a positive function, lower sum is kind of an underestimate for the area under the curve, and the upper sum is sort of an overestimate for the area under the curve. Okay. As you can see here also, when you make your delta x to be smaller, delta x means the width of a rectangle. Okay, delta x is always the width of a rectangle. When you make your delta x smaller, you get better and better approximations. This is the approximation when you have 50 rectangles, and this is the approximation when you have 100 rectangles. As you can see, this looks like almost a perfect approximation. Okay. All right, so that's what we were discussing in the previous section. In this section, we want to develop a method to find the exact area under this curve. As you can see, when I make my delta x smaller or the width of the rectangles smaller, I get a better and better approximation, right? This looks almost a perfect approximation for the area under the curve. So then what do I have to do to get an exact answer? All I have to do is I have to send this delta x to 0. If I want to send my delta x to 0, I'm going to have to send n to infinity. As n approaches to infinity, this quantity approaches to 0, right? That's what exactly I want. I want to make my delta x as small as possible. For that, I want to send the limit of n to infinity. Okay, that way we will get 1 over n tends to 0. That's the idea. That's the motivation. Now let's define definite integrals formally. Okay, here is the first definition we have. Definition 4.9. The definite integral of a function on an interval We are going to define the definite integral of a function on an interval. Let f be a function defined on an interval a comma b. Then it should be then definite integral of f from x is equal to a to x is equal to b is defined to be the number. Here is how we denote the definite integral from a to b. You write this symbol. This is called the integration symbol. This symbol is called the integration symbol. You write that symbol and then you put the lower limit here a and the upper limit here b. Lower limit means this left endpoint. The upper limit is the right endpoint. And these are called the limits of the integral. Okay, integration. And here is how you denote the definite integral from a to b. Okay, and it is defined by this number. What you do is, this is the Riemann sum that we defined last time. Sigma k goes from 1 to n f of xk star times delta x. Of course, your delta x is defined by this expression. We all know that. And this xk star is a number between xk minus 1 and xk. Okay. Then what you do is, that is the Riemann sum, and then you take the limit as n goes to infinity. Okay, you take the limit of this expression as n goes to infinity to find the definite integral from a to b. Okay, if your function is a positive function, this limit gives you the area under the curve between a and b. Okay, all right, and then here we have a small remark. What that tells you is that we say that this function f of x is an integrable function on the interval a comma b if this limit exists. Okay, if this limit exists, we say that the function f is integrable on the interval a comma b. All right, let's move on. That's how we define definite integral of a function. Let's look at an example to understand what's going on here. Consider again the example. This is the first example that I showed you actually. This example. Okay, we'll consider that example one more time here. For any given n, if you consider this example, for any given n, we know that delta x is always b minus a over n, which is 1 over n. Your b is 1 in this case, a is 0. So b minus a is 1 divided by n. Your delta x is 1 over n. And of course, your xk is a plus k times delta x. That is a. A is 0 because your left endpoint is 0 plus k times delta x means k divided by n. This whole thing is k over n. So we have xk is k over n, and delta x is 1 over n. Okay. Now, how do we define the definite integral from 0 to 1? That is denoted by definite integral of f from 0 to 1 is denoted by integration 0 to 1. You put the upper bound and upper limit and the lower limit like this. This is the upper limit. This is the lower limit. F of x dx. That means the definite integral of f of x from 0 to 1. That is defined by the limit of this summation. Summation k goes from 1 to n f of xk star times delta x. Okay. All right. Can we really find the definite integral using the formula? Of course we can. What we need to do is to find this definite integral. All I have to do is I need to find this limit. Okay. When I find this limit, remember this xk star is any number in the interval xk minus 1 comma xk. So to find this limit, I'll take xk star to be the right endpoint. That way I get the right sum here. Okay. So let's see if we can find the definite integral. This is going to be equal to limit as n approaches to infinity pardon me, not the summation, limit as n approaches to infinity, sigma k goes from 1 to n, f of, I'm going to take my xk star to be xk. I'm taking the right sum here, times delta x. Delta x is your, this is, delta x is 1 over n, okay? All right, now if you simplify this a little bit further, you get limit as n approaches to infinity, limit as n approaches to infinity, sigma k goes from 1 to n, f of xk. Remember, your xk is k over n. To find f of xk, you plug in xk in your function. Then you get k over n squared, because your xk is k over n. You plug in k over n in your function, you get k over n squared times 1 over n. That's what you have. Okay. Now let me simplify this a little bit further. Then you will get, if you simplify your expression, limit as n approaches to infinity, sigma k goes from 1 to n, k squared divided by n cubed. Here you have n squared in the bottom. If you multiply that n squared with this n, you get n cubed. Okay. Of course, in the top you have n squared. Now what I'm going to do is, here the running index is k. K is what is varying. N is a fixed number here. Okay. So at least here in this expression, n is a fixed number. So I can pull out 1 over n cubed. Okay. So this will give me limit as n approaches to infinity, 1 over n cubed times sigma k goes from 1 to n, k squared. Okay. Now I can use the sigma formula for this one. I know a formula for the k squared. Sigma k goes from 1 to n, k squared. I have a formula for that. Here is the formula. Okay, n times n plus 1 times 2n plus 1 divided by 6. So let me use that formula over here. So this whole thing will be equal to limit as n approaches to infinity, 1 over n cubed times n plus 1 times n plus 1 times, let me write n times n plus 1 times 2n plus 1. Okay. Now all what you need to do is to take the limit of this expression. How do you take the limit of this expression? Okay. Let's see how we can find the limit of that expression. Okay. Here is what you have. What I'm going to do is limit n approaches to infinity. I'm going to simplify this a little bit. I'm going to simplify my top first. Pardon me, here you should have 6 underneath of this. Okay, in the formula, you should have a 6 underneath of here. All right, so you have 6 underneath here. Okay, so what I'm going to do is, now I have this expression, I can FOIL this one. Okay, I can expand this expression and I get, if I expand this expression, I get this expression, 2n cubed plus 3n squared plus n. And in the bottom, you have 6 times n cubed, which is 6n cubed. Now to find the limit, I'm going to divide each individual term by 6n cubed. Limit n approaches to infinity, 2n cubed divided by 6n cubed plus 3n squared divided by 6n cubed plus n divided by 6n cubed. Okay. Now, if you simplify this a little bit further, you will get limit as n approaches to infinity. You get 1/3 here, plus here you get 1 over 2n, plus here you get 1 over 6n squared. As you can see, as n approaches to infinity, these two will be going to 0. So only remaining thing is 1/3. So your answer is 1/3. This is the exact area under the curve f of x is equal to x squared on the interval 0, 1. Remember, the graph looked like this: 0, 1. This is y is equal to x squared. 1/3 is the exact area under the curve in the interval 0, 1. Okay, so that gives you that definite integral. This definite integral gives you the area under the curve in this case, because it's a positive function. Okay. All right, let's move on. And then we have this theorem, theorem 4.10, definite integrals measure signed areas. Okay, what do you mean by signed areas? Okay, so let's go over this theorem that will answer that question. What we mean by signed area. Definite integral counts area above the x-axis positively and area below the x-axis negatively. Algebraically, this means that if f of x is greater than or equal to 0 on an interval a comma b, then the definite integral of f of x from a to b is always greater than or equal to 0. And if f of x is less than or equal to 0 on a given interval c comma d, then the definite integral, this bound should be, this is c actually, this is d. Okay, if your function f of x is less than or equal to 0 on an interval c comma d, then the definite integral of f of x from c to d, is always less than or equal to 0. Why is this true? Okay, as you can see here, if your function is positive, first of all, notice that this is the definition of definite integral from a to b. Definite integral from a to b is defined by limit as n goes to infinity, sigma k goes from 1 to n, f of x star times delta x. As you can see, if your function f of x is greater than or equal to 0 on this interval, this number is greater than or equal to 0, because you pick this xk star from this interval, which is a sub-interval in the interval a comma b. Okay, we know that in this entire interval, your f of x is greater than or equal to 0. That means this number is greater than or equal to 0 for any xk star. And we also know that delta x is b minus a over n. Of course, if a comma b is an interval, b is bigger than a. So this is positive. This whole thing is positive. So this is a quantity which is greater than or equal to 0. So this summation is greater than or equal to 0. So our limit is also going to be greater than or equal to 0. That means our definite integral is greater than or equal to 0. By a similar argument, if your function f of x is less than or equal to 0, then think of, you have c here and d here. Then this expression, look at this expression. If your f of x is less than or equal to 0 on this interval c comma d, this number is less than or equal to 0, because your function is less than or equal to 0 on the interval c comma d. And delta x is of course positive, because it's c minus d over, in the second case, delta x is c minus d over n. That is positive, pardon me, d minus c over n. Okay, in the second case, delta x is equal to d minus c over n, which is clearly positive because d is bigger number. D is the bigger number. Okay, and this is a number which is less than or equal to 0. This is a positive number. This whole thing is less than or equal to 0. That means the summation is less than or equal to 0. As a result, this limit is less than or equal to 0. That means this definite integral from c to d. In the second case, we have c to d. Okay, this definite integral is less than or equal to 0. That's the idea. That means if your function is below the x-axis, the definite integral is less than or equal to 0. And if your function is above the x-axis, the definite integral is greater than or equal to 0. That's why we say that it measures the signed area. Okay, geometrically, if we have a function like this, 0 to let's say 2, then let's say this is the function f of x. Then the definite integral from 0 to 2 f of x dx is greater than or equal to 0 because this function is above the x-axis. It gives you this area. Okay. If your function is below the x-axis, say like this, again 0 to 2, this is your f of x this time. Then 0 to 2, f of x dx is less than or equal to 0. You get this area as a negative number this time. You will get the magnitude. Magnitude of that negative number is exactly this area, but you will get that as a negative number if your function is below the x-axis. All right, let's move on. Next, I want to go over this theorem, theorem 4.11. Sum and constant multiple rules for definite integrals for any functions f and g that are integrable on a comma b and any real number k. Okay, here is the first statement, first part. Definite integral of f of x plus g of x from a to b dx is given by definite integral of f of x from a to b plus the definite integral of g of x from a to b. Okay, what it tells you is that you can distribute this integral sign inside the parentheses. You can take the definite integral of f of x and then plus the definite integral of g of x. Okay, this is kind of similar to the sum rule for the summations. Okay, in summation formula also we use a similar result. So basically your definite integral symbol is kind of a distributive. You can distribute this inside the parentheses. And then the constant multiple rule, what it tells you is that the definite integral of k times f of x, k is a constant, k times f of x from a to b is the same as k times the definite integral of f of x from a to b. Okay, simply what that tells you is that you can pull this constant out. If you have a constant, you can pull that constant out and take the definite integral of the remaining function. Okay, all right, let's go over our next theorem, theorem 4.12, properties concerning limits of integration. Okay, this is also a very important theorem. If a is less than b are real numbers and f is integrable on the interval a comma b, then we have these results. Part A, the definite integral of f of x from a to a. Okay, a to itself, f of x is equal to 0, and then definite integral from b to a. Definite integral of f of x from b to a is equal to minus times definite integral of f of x from a to b. What this tells you is that you can switch these limits by putting the minus sign in front. Okay, that's what that result tells you. And then further, we have this result. If c is any real number in the interval a comma b, here is the picture. You have a here, b here, c is somewhere in that interval. C can be the endpoints as well. Okay, c is somewhere in that interval. Then we have this result. The definite integral of f of x from a to b is equal to definite integral of f of x from a to c plus the definite integral of f of x from c to b. What you do is you take, if you want to take the definite integral from a to b in this entire interval, what you can do is you first take the definite integral in this interval from a to c, that is this one, and then you take the definite integral of the remaining part. Remaining part is from c to b, the definite integral from c to b, and then you add them together to get the definite integral on this entire interval from a to b. Okay, that's the idea of the third part. Okay, actually all these parts can be proven using the definition. They are very straightforward, just unwinding the definition, so I'm not going to prove it. All right, now let's look at some applications of this theorem. Okay, here is the application I want to look at. Given that the definite integral of f of x from 1 to 3 is 4, and then the definite integral from definite integral of 2 times f of x from 5 to 3 is equal to -3, and we are asked to find definite integral of f of x from 1 to 5. Okay, how do you find this? How do you find this particular definite integral? From the previous theorem, I have this particular result. I can find a definite integral from a to b this way by splitting that into 2 integrations. That's what I'm going to do here. Okay. In order to find this one, this integral, this is my goal. I want to find 1 to 5. Let me write. Want to find definite integral from 1 to 5 f of x dx. Okay, this is equal to definite integral from 1 to 3 f of x dx plus definite integral from 3 to 5, the remaining part. Okay, first I go from 1 to 3. Remember that my original interval is 1 to 5. So I go from 1 to 3 first, and then I go from 3 to 5, the remaining part of the interval. Okay, f of x dx. But the good thing is this quantity is given. This is here. I just have to figure out this quantity. If I can figure out this quantity, I'm done. Okay, how do I figure out this quantity? This is not exactly given, but something similar to that is given here. See, I need the definite integral of f of x from 3 to 5. Here it is given. Here we are given a definite integral from 5 to 3, but we have a 2 in front. We need to deal with that as well. But we can find this particular definite integral using this data and using this theorem. Okay, in particular using this part of the theorem. And of course, we are going to use the constant multiple rule as well. Okay, so let's see how to handle this one. So I'm going to do some modifications here. I'm going to do some calculations here. So this is what I'm given. 5 to 3, definite integral from 5 to 3, 2 times f of x dx is given to me, which is -3. Now using the constant multiple rule, since this 2 is a constant, I can pull this 2 out. Okay, that is the constant multiple rule that we discussed in theorem 4.11. So let's do that. If I do that here, I get 2 times 5 to 2, 5 to 3, pardon me, f of x dx is equal to -3. That will give me 5 to 3 f of x times d of x. F of x d of x is equal to -3 over 2. I divided both sides by 2. I'm almost there. Okay, I have the definite integral of f of x from 5 to 3, but what I want is the definite integral of f of x from 3 to 5. I can easily adjust this to get this definite integral. What do I have to do? I just have to apply the second part of this theorem. I know that the definite integral from b to a f of x dx is same as minus times definite integral of f of x from a to b. So this should be equal to by part B in theorem 4.12. In theorem 4.12, we have definite integral of f of x from 3 to 5 f of x dx is same as minus times the definite integral of f of x from 5 to 3. 5 to 3 f of x dx. But I know this quantity now. I know this quantity. Definite integral of f of x from 5 to 3 is -3 over 2. I can plug in -3 over 2 here to get what I need. So then you get minus times -3 over 2, which is +3 over 2. Okay, so we have this value. this value, definite integral of f of x from 3 to 5, which is 3 over 2. Now we can calculate this number. Definite integral of f of x from 1 to 3 is given, which is 4 plus 3 over 2, which is 11 over 2. Okay, that completes that example. All right, let's move on. Next, we have this particular theorem. This is a very important theorem in this section. Theorem 4.13, definite integral formulas. Okay, for any real numbers a, b, and c, we have these formulas. Part A, the definite integral of c. C is a constant from a to b is equal to c times b minus a. And then the second part, the definite integral of x, your function is x this time, from a to b is b squared minus a squared divided by 2. Part C, the definite integral of x squared from a to b is equal to b cube minus a cube divided by 3. Okay, I'm not going to prove all these formulas, but I'll prove one of these formulas. Let's prove part A. Prove part A. Okay, we know that by the definite integral formula, the definite integral of f of x, we know that the definite integral of f of x from a to b is defined by this quantity. The limit as n goes to infinity, sigma k goes from 1 to n, f of xk star times delta x. Remember, this xk star is a number between xk minus 1 and xk. Okay, so let's see if we can prove that the definite integral of c dx is equal to definite integral of c from a to b is equal to c times b minus a. So let's apply this formula. Okay, so I get from this formula definite integral of c from a to b dx is equal to limit as n goes to infinity, limit as n goes to infinity, sigma k goes from 1 to n, f of xk star. What is my f of xk star? Notice that my f of x is a constant this time. Then f of xk star is z. It doesn't change because my function is a constant function, times delta x. What is delta x? Delta x is always b minus a over n. Okay, now this is equal to limit n goes to infinity. I have noticed that this whole thing is a constant in this case because the running index is k. There is no apparent k here, right? So I can pull this whole thing out. Okay, so let me pull out that term. You get c times b minus a divided by n, and then you have sigma k goes from 1 to n, just 1. But what is k goes from 1 to n? 1, which is n by the summation formulas that we learned. Okay, so I can put n there. Then you get c times b minus a divided by n times n. And this n and n are cancelled. You get c times b minus a as required by the formula. Okay, that's what we wanted to prove. C times b minus a. Okay. Likewise, you can prove the other formulas as well using the definition. You use this definition to prove these formulas. All right, let's move on. Okay, next I want to work on this particular example. find n rectangle right sum approximation for this particular integral. Okay, so let's try to find the right sum approximation. First of all, we know that the right sum, n rectangle right sum approximation is given by, all right, right sum sigma k goes from 1 to n f of xk times delta x. Okay, when you take the right sum, your xk star should be xk. Okay, in the right sum case, your xk star should be equal to xk. Okay, that's from the previous section. Okay, how do we find this sum then? First of all, we need to find xk and delta x, right? So how do you find delta x? My delta x is b minus a over n. B is 4 minus 2. Notice that your b is 4, a is 2. So 4 minus 2 divided by n, which is 2 over n. Xk is, we know that xk is a plus k times delta x, which is 2 plus k times delta x, which is 2k divided by n, because your delta x is 2 over n. So this is xk. Okay, so we found xk and delta x. All right, then my right sum is equal to, I'll write rs for the right sum, is equal to sigma k goes from 1 to n f of xk. To find f of xk, notice that my f of x is x squared plus 1. Let me write it here. My f of x is this expression. Okay, x squared plus 1. Now I can find f of xk by plugging my xk in the function f of x. My xk is, of course, 2 plus 2k over n. Okay, so you get 2 plus 2k over n squared plus 1, that is f of xk, times delta x. Delta x is 2 over n. Delta x is 2 over n. Okay, now all I have to do is to simplify this expression. Okay, if I simplify this expression and if I distribute this n inside, then you will get sigma k goes from 1 to n 8k squared over n cube plus 16k divided by n squared plus the last term is 10 divided by n. That's what you get. Okay. Now I'm going to distribute this sigma notation inside the parentheses. Okay. I can do that using one of the summation rules that we learned in section 4.1. Okay. If I do that, okay, I send the sigma sign, sigma notation over to this expression, then you get 8 over n cubed times sigma k goes from 1 to n k squared. Notice that in this expression, if I apply the sigma notation to this expression, this 8 and n are constant, n cube are constant. So I can pull this term out, 8 over n cube. That's how you get this 8 divided by n cube in the front. Because the running index is k, you have k only in this term, which is k squared. So I'm leaving the k squared as it is and pulling the rest of the thing out. And then I send this, I put this sigma notation for the second term here. Again, I'm going to pull out constant terms. 16 divided by n squared times sigma k goes from 1 to n k. Finally, I have 10 divided by n sigma k goes from 1 to n 1. Notice that here this is a constant. There is no k here. So I can pull that out. I just have sigma k goes from 1 to n 1. Okay. All right, that's what I get. Now what I can do is, now I can use formulas. I have a formula for sigma k squared, sigma k, and sigma 1. Okay, so let's apply those formulas. If you apply the formulas, you get, okay, if I apply those formulas, this is going to be n times n plus 1 times 2n plus 1 divided by 6. And this is going to be n times n plus 1 divided by 2. And this is, of course, n. Okay. Now I can simplify this a little bit further. You have 8n divided by 8n times n plus 1 times 2n plus 1 divided by 6n cubed plus 16n times n plus 1 divided by 2n squared plus 10n. Of course, these two are cancelled. N and n cancel. You just have 10 there. You have just 10 there. Okay. All right. This is what you have. This, the n rectangle right sum is given by this formula. Okay. Next, we are asked to find the n rectangle right sum when n is equal to 100. First, when n is equal to 100, and then when n is equal to 1000. All what you need to do is you plug in n is equal to 100 in this formula. And then to find the n rectangle right sum with n is equal to 1000, you plug in n is equal to 1000 in this formula. Okay. I'll write right sum with n is equal to 100. I plug in 100 in this formula. 8 times 100 times 101 times 201, because 200 times 2 times 100 plus 1, which is 201, divided by 6, not 6, 6 times 100 cube. It should be n cube in the bottom, plus 16 times 100 times 101 divided by 2 times 100 squared plus 10. Okay. And if you compute this value using a calculator, you will get 20.7868. Okay. Okay, this is the right sum with 100 rectangles. And if you similarly compute the right sum with 1000 rectangles, you will get 20.6787. Okay, so that gives you the answers. And then finally, we are asked to take the limit as n approaches to infinity of n rectangle right sum to calculate this integral. Okay, so this is the right sum formula. And we started with this formula. Remember, we started with this formula. And if I take the limit as n goes to infinity, okay, by the definition of definite integral, we get the definite integral, the value of the definite integral from integral of f of x, which is x squared plus 1 from 2 to 4. Okay, that's the definition. If I take the limit as n goes to infinity, that should give you this definite integral by definition. Okay. All right, so let's calculate the definite integral by taking the limit here. All right, I have copied down the right sum formula here. In rectangle right sum is given by this formula. Now to find the definite integral of x squared plus 1 from 2 to 4, all I have to do is I need to take the limit of this expression as n goes to infinity. Okay, so that means I have to take the limit of this expression. So this is equal to, this definite integral is equal to limit as n approaches to infinity 8n times n plus 1 times 2n plus 1 divided by 6n cubed plus 16n times n plus 1 divided by 2n squared plus 10. You need to take the limit of this expression. Okay, if you take the limit of this expression, you can see that can see that the limit of this first expression is going to be 16/6 plus the limit of the second expression is going to be 16/2. And of course, the limit of the last expression is 10, which is a constant. Okay. And if you simplify this, you will get 62 divided by 3. That's going to be the answer for your definite integral. Definite integral of x squared plus 1 from 2 to 4. Okay. All right, let's move on. Let's go over this example now. Use properties of definite integrals and the definite integral formulas in theorem 4.13 to verify the calculation of this definite integral. Definite integral from 2 to 4, x squared plus 1 dx is equal to whatever the value we found. We need to show that it's 62/3. Okay. What are the formulas in theorem 4.13? Here are the formulas. Here is the theorem 4.13. We have these formulas. Okay. Which formula am I supposed to use here? My function is x squared in that case. Actually, not x squared plus 1. I can use some of these formulas to calculate that definite integral. Okay. This definite integral. This is what I wanted to calculate. Okay. Let's see how we can apply these integral formulas. Here, let's notice few things. If I go back to my example, notice that my a is equal to 2, b is equal to 4. That's clear. A is the lower bound, b is the upper bound. Okay. Now, I'm going to apply some of the integral formulas that we discussed. Integration of x squared plus 1 from 2 to 4 dx is equal to, remember, this is a summation of two functions. So I can distribute this definite integral inside. Okay, then we get, that's the sum rule. Okay, sum rule for definite integrals. Definite integral of x squared from 2 to 4 plus the definite integral of 1 from 2 to 4. I'm just distributing this integral symbol inside the parenthesis. Okay, that's the sum rule for definite integral. All right, now how do I find these two integrals? That's where theorem 4.13 is going to help us. Okay, in theorem 4.13, we can find the definite integral for this expression using this formula. I can use this formula to find the definite integral. Okay, so let me copy that formula over there. All right, I copied down those formulas over here. We know that the definite integral from a to b, x squared dx is equal to b cube minus a cube divided by 3. Okay, that's what we have here. Okay, your a is 2, b is 4. You have x squared. So I can apply that formula to find this definite integral, this particular formula. Okay, so that would be equal to b cube minus a cube divided by 3. B cube is 4 cube minus a cube. A cube is 2 cube. 2 to the power 3 divided by 3. That's the first integral. The value of the first integral, first definite integral is this one. And then how do I find the value of the second definite integral? Well, here this is a constant, right? If you have a constant as your function, if you have c, then the definite integral of c from a to b dx is c times b minus a. Notice that in this case, your c is just 1. So the answer should be 1 times b minus a. B minus a is 4 minus 2. Okay. If you calculate this, you will again get 62/3. That is what you got in the previous part. Okay, 62/3 using the right sum formula. Using the right sum formula, and of course, you took the limit as n goes to infinity in the right sum formula to calculate that definite integral. Okay. All right, let's move on. Next, I want to go over this particular example. use a graph and properties of definite integrals to argue that this particular definite integral is negative. Then find a number a such that this definite integral is exactly 0. Okay. How do we argue that this definite integral is negative? First of all, notice that my f of x in this case is 2 minus x. This is my f of x. Okay. Now, if I graph my f of x on the interval 1, 5, because I'm concerned about the interval 1, 5, because my definite integral is from 1 to 5. Okay. So if I graph my f of x on the interval 1 to 5, you will get a graph like this. Okay. All right. Now, notice that from the previous theorem, we know that from a previous theorem that we discussed today, we know that definite integral of 2 minus x from 1 to 5 is the same as I can take the definite integral from 1 to 2 and then from 2 to 5. First you take 1 to 2 and then 2 to 5. This is equal to definite integral from 1 to 2, 2 minus x dx, plus the definite integral from 2 to 5, 2 minus x dx. Okay. As you can see, this function is positive from 1 to 2, or your function is above the x-axis from 1 to 2, and your function is below the x-axis from 2 to 5. Okay. Notice that the definite integral will count the region above the x-axis positively and the region below the x-axis negatively. That means you will count this region positively and this region negatively. As you can see, this area is bigger. Okay, this area is smaller. So you have a larger negative number and a smaller positive number. Okay, so this will be a smaller positive number and this will be a larger negative number because this area is bigger, okay, than this area which is considered positive. So this whole thing will be negative as a result of that. All right, next, how do we find a number a such that the definite integral of 2 minus x from a to 5 is exactly 0? Well, if you want your definite integral to be 0, that means the area above the x-axis in that interval, on the interval a to 5, a comma 5, you should have the area above the x-axis is same as the area below the x-axis. That means you need to find your a somewhere here, somewhere in this, somewhere to the left of 5, so that the area above the x-axis is same as the area below the x-axis. For example, if I take my a to be here, a to be minus 1, then as you can see, the area above the x-axis is this area, and that area is same as this area by symmetry. You can clearly see that by symmetry. If I take negative 1 to be your a, your interval of concern is 1 minus 1 to 5. In that case, if you take the area above the x-axis, that is this area, that area is same as the area below the x-axis. So those two areas will be cancelled because this area is counted as a positive area and this area will be counted as a negative area. They will be cancelled when you take the definite integral. So the number that you need to choose so that this definite integral is 0 is a is equal to minus 1. It is just by observation. A is equal to minus 1. If you choose a to be minus 1, you get the area above the x-axis is the same as the area below the x-axis on that particular interval minus 1, 5. Okay. Okay, that means a is equal to minus 1 will give you definite integral from a to 5, 2 minus x dx is equal to 0. That's basically because in that interval minus 1 to 5, the area above the curve is the same as the area below the curve. So the area above the curve is counted as a positive area. Area below the curve is counted as a negative area. They will be cancelled to each other and will give you 0. All right. With that, we conclude section 4.3. I will stop there and I'll see you next time.